Okay, so let's start. So we were talking about DC to DC buck converter, right? We talked about one of the applications for DC to DC buck converter, which was in electric vehicles stepping down from 48 or 50 volt to 12 volt to run all the auxiliary systems on the vehicle, right? Like lights, fans, everything. And we saw that all the loads may not be on all the time, right? So sometimes you may have more load, sometimes you may have less load, and depending on the load, your average load current will change, and therefore your average inductor current will also change, right? And therefore we saw that if this is your inductor current, it could be like this. If the load reduces, this may reduce to this. If the load further reduces, it may reduce to this, and beyond this, this goes in discontinuous conduction mode, right? So these are CCM, continuous conduction mode. Beyond this, it goes in discontinuous conduction mode, wherein your inductor waveform may look something like this. Right? It may come to 0 before the completion of the cycle, before Ts, and then it may remain at 0. This is what we saw last time, right? So this is dTs, this is Ts. This point is a new point now. Let's just write it as gamma times Ts, where gamma is less than 1, right? Let me also draw a buck converter so that this is the load resistance, this is capacitor, inductor, diode, switch, input voltage and output voltage. Okay. Now first thing what we will do is we will derive a condition so that we can identify whether the converter is operating in CCM or it is operating in DCM, right. So as you see, this is the limiting case, this is the boundary between continuous conduction mode and discontinuous conduction mode, right. In this case, the average inductor current in this case, let me put it as the star mark. So the average inductor current in this limiting case is nothing but equal to delta IL by 2, where delta IL is nothing but this peak to peak value. Delta IL is this peak to peak value is what is referred as delta IL, right, in this limiting case. Of course, if your current moves further upward, then delta L by 2 will remain the same, but then your average of the current will keep on increasing, right. And if this guy goes below this, that means you are in discontinuous conduction mode, right. So this is in a way the limiting condition. So what we will do is we will try to calculate the relationship for this condition, and then we can put an inequality saying that, you know, if you are above this, then you are in CCM, if you are below this, you are in DCM. So for this limiting condition, the average inductor current is equal to delta IL by 2. You can write average inductor current as the output voltage upon the load resistance RL is equals to delta IL by 2. Delta IL is nothing but equal to, what was delta IL expression? Some Vn minus Vo into D times Ts upon 2 will come here and probably L, right. This was the expression for delta IL that we derived in previous class. Is that correct? Can someone cross check? Any questions so far? Yeah, so we'll come to that. In this case, we'll come and we'll analyze this case in more detail very soon in the next board, just few more minutes. But nevertheless, you can see, right, in this case, if your average current is more than or equal to delta L by 2, that implies you are in CCM, right? That part you are sure, you agree, right? I agree that you may be thinking what happens here, and we'll analyze it in a little bit more detail. But certainly if delta L is greater than, if average current is greater than delta L by 2, right, you are confident that this is in CCM, right, there is no question about it. So let us just find this condition and then we will see that how this thing changes. So if you solve it, what do you get? Let me put this as a greater condition here for CCM. You can take RL on that side, then substitute things, and you would get RL to be less than V naught. Now since V naught I can substitute as D times Ts for this case, because it's same as continuous conduction mode, some things will cancel out. Right, 2 times L divided by 1 minus D times Ts. That makes sense. Just check if this is okay. Have I missed something? So if your load resistance is less than this, that means you are in continuous conduction mode, right? If a load resistance is less than this, that means your load is more, right, higher current, then you are in continuous conduction mode. We also call this right hand side expression as critical resistance, right. So this we can call it as R critical, which means nothing but that your resistance, if it is less than critical resistance, you are in continuous conduction mode. Is that okay? Any questions? Alright. Now let us go. Okay, so let me just repeat what he said. So what he is saying is, in this case, by that you mean the discontinuous conduction mode. He is talking about the critical case. This is the critical conduction mode, right, the last waveform which I have drawn, the bottommost. He is saying the output voltage varies, or rather has a large amount of ripple. Is that what you are saying? Okay, so let us say this is case 1, this is case 2. So in case 1 versus case 2, in which case would your output voltage ripple be higher? This is the question, I am just rephrasing it. So think of it as a quiz question. So case 1, case 2, case 1, case 2, in which case would the output voltage ripple be higher? Let's answer this, then we'll go to the next question. In which case would the output voltage ripple be higher? Case 1 versus case 2, in which case the output voltage ripple delta V naught be higher? You don't have to look at the expression which you derived last time. You can do that, that's an option. Just see the formula and then you can figure out, or don't see the formula and you just think over here, right? You remember the current source here, you remember the current source here, you remember the ripple current going in the capacitor. In which case would the ripple current be higher? 1, how many of you say 1? 1 for 1, okay. How many of you say 2? At least we should have 2 people. 1 more. Okay, then what is everyone else's answer? It remains the same, right? So ripple, because the ripple current is the same, the average current anyways goes from here to here. Since the ripple current component is the same, that's what is flowing here and that's what is leading to the ripple in the voltage. So that remains same, means ripple in the output voltage would remain same. Anything else? Okay, so another question, case 1, case 2, what would be the average output voltage in case 1 versus case 2? So delta V remains the same, right? Case 1, case 2, delta V same. What is the average output voltage in case 1 and case 2? Then what are you saying? Okay, let me just complete since I have asked this question. So what is the average voltage in case 1, case 2? Are they equal? Yes. No? No? Why no? value of resistance is different. Absolutely, but the resistance is also different, right? So if you remember, we derived the expression, assuming these components are ideal, we derived the expression V out is D times V in. That expression we derived for this case, but nothing has changed going from case 1 to case 2. On the x-axis still, you know, switch is conducting for this duration, diode is conducting for this duration. You have across the inductor, you have positive voltage in this duration, V in minus VO. You have a negative voltage here, which is minus VO. So nothing has changed. So the expression for 1 and 2 remains the same. Of course, it would change if we go to case 3, and which is what we will see now. But for 1 and 2, your output voltage expressions, your ripple current expressions, everything remains the same what we have derived. So that remains the same. Okay. Anything else? Okay. The out can be written as RL times IL average, okay? No, that's what I am saying, right? Your converter is producing the voltage and the current is determined by the voltage. The voltage is constant from case 1 to case 2. You are changing the load resistance, current is changing accordingly. V by R. Any more questions? Okay. The problem is if you go from case 2 to case 3, everything changes, right? Your ripple expression would no longer be valid, your average voltage expression would also no longer be valid, right? So everything would change from 2 to 3, but 1 to 2 everything is same. And we know the condition, if your load resistance is less than this critical value, then you are moving into discontinuous, then you are in continuous conduction mode. If load resistance is more than this, you are going towards discontinuous conduction. Let's just understand the relationship once before we go and derive the expressions for 3. So the critical resistance is equals to 2L by 1 minus D times Ts. That means if you have higher inductor, higher value of L, your critical inductance would also be higher. That means your converter can operate in CCM further till a lighter load condition. Is that okay? So higher inductance, of course, higher inductance means the ripple is small. So it can remain in continuous conduction mode for even at a lighter condition, relatively speaking, right? Or if your switching frequency is higher, it can remain in continuous conduction mode for even further lighter condition, right? Is that okay? This is the relationship predominantly with L and Ts. We understand D you would fix based on the average voltage requirement, right? Okay, now let's move to this board and let me just draw the converter again. Zero Ts, dTs and gamma Ts. For time period from 0 to dTs, your switch S is on, right? From 0 to dTs, your switch S is on, current is flowing in this direction, right? The voltage across inductor is given by V in minus VO. Is that okay? Same, whatever was happening before. Is that fine? From time period dTs to gamma Ts, your S is off, but then the current will continue to flow through the diode, because current doesn't, if this switch is open, this current has no path to flow from here, and therefore it would continue to flow through this diode. And in that case, diode is on or conducting, and VL is equals to minus V naught, where VL reference is this one. Okay. So this was the same case as before. Now there is one more period where the inductor current is 0, and that period goes from gamma Ts to Ts, and in that case S is off, diode is in this case. So this current was flowing, it came to 0. Naturally, instead of diode, if you had a short circuit, current would have reversed, but now because it's a diode, current cannot flow in reverse direction. So there is no option but for this current to become 0 and remain at 0, and therefore this diode is open, right? This diode is open now. So this is open, this is open. What is the voltage across inductor now? So diode is open, switch is open, what is the voltage across inductor? What is voltage across inductor? What is voltage across inductor? What is voltage across inductor? Voltage across inductor? 0. Okay. Voltage across inductor is 0, because if there is an inductor, there is no current, voltage has to be 0, right? There is no current, there is no di by dt, nothing, it is just 0. Okay. So we have 3 conditions here. This one, and the third one. And now what we will do, if I want to find relationship between the input and the output voltage, I can still apply, is this circuit in steady state by the way? Can I apply volt second balance? Can I apply volt second balance? Is this in steady state? Okay, so I can apply volt second balance, I can equate average voltage of inductor to 0, and if I do that, I can write V in minus VO is applied for a duration of d times Ts plus minus VO applied for a duration of gamma minus d times Ts plus 0 applied for a duration of 1 minus gamma times Ts equals to 0. If you solve it, you would get VO by Vin is equals to d upon gamma. And try to solve it, see if you get it or not. Okay, so you asked me the question that if I can repeat the part where diode turns off, right? So from in the second period, the diode is on, right? So the equivalent circuit is just this one. So you have an inductor, you have a voltage which is almost a stiff voltage source, which is applying minus V naught. Inductor current is falling. Now inductor current has come to 0. Now what can happen? 3 things can happen. Inductor current can go to negative, inductor current remains 0, inductor current can again become positive. Can inductor current become, this is not on, this is still off. So can inductor current become positive? No, because for inductor current to become positive, the voltage across inductor must be positive, which doesn't seem to be happening. Can inductor current go negative? No, because diode will not allow it to do that. So the only option left is current will just remain at 0. Is this expression fine? Any doubt here? And now with this expression you can think a lot, right? You can think about the output voltage average value, you can start thinking about the slopes of the line that we have drawn, right. Now assume that there was a converter was operating, right, and I have slowly started increasing the load resistance, and I increased it little bit, I moved from the earlier case 1 to case 2, the output voltage remained same. But now I further increase the load resistance, that means reduce the load current. Then I move from 2 to 3, this is 3, right, this is the 3 waveform. While going from 2 to 3, would the output voltage change? While going from 2 to 3, would the output voltage change? Yes. Will it increase or will it reduce? Will the output voltage increase or will it reduce? While going from 2 to 3, will the output voltage increase or will it reduce? It will increase, right? Because this earlier expression was d by 1, now you have gamma, gamma is clearly less than 1. So the output voltage must be more than the previous case, right? And now it's even more difficult because it depends on gamma. So you further, you go from case 3 to case 4, your gamma will change, your output voltage will change. So throughout CCM, your output voltage was more or less constant, but as soon as you reach the DCM, your output voltage is going to change with gamma, and therefore you can no longer maintain a constant duty cycle, you have to keep adapting the duty cycle based on the load, right. Earlier also, in reality, there may be small variations, but not that much, but in discontinuous conduction mode, certainly you would have a large variation of duty cycle, isn't it? And therefore, in reality, all these converters have to have a closed loop kind of an operation, where the duty cycle gets adjusted based on observation of the output voltage, right. So if you see output voltage becoming 60, you adjust the duty cycle, still the relationship is the same, that if you reduce the duty, the output voltage comes down, thank God, right, doesn't change. So it's still a same relationship, but the factors will keep on changing. So if your output voltage goes to 60, you bring it down to 50, right. All of you have done the basic control systems course, right. So think of this system as a plant, and now you have to have a controller for this system. Okay, sure. Okay, any doubt here? Yeah, of course, this course is not an advanced course, so we won't really go into details of how do you do the closed loop control of this system and how do you model it in more details. Those things we don't do, but you get a flavor of things that you cannot just keep a fixed duty cycle and this would work. And any application if you pick, there would be a closed loop system to control these power electronic converters. Very rarely, you would have systems where there is no closed loop, very, very rarely. But you can figure out in those cases or in those systems, you must operate always in CCM first of all, because as soon as you go in DCM, there is a huge correlation between duty cycle, there is a huge correlation between the load and the output voltage, right. So, but those are very, very rare systems. Most of the practical systems are to be operated in closed loop. Okay. Now the question is, if I give you a numerical, right, how would you solve for output voltage? Because you don't know gamma. Earlier you knew Vin, duty cycle, so you could quickly calculate. Now you don't know gamma, so how will you calculate the output voltage? So if you have to calculate the output voltage, you know the information of gamma. Gamma depends on the load, right? Because if your load resistance is keeps on changing, your gamma keeps on changing. So what we do is we write another equation which correlates the gamma with the load resistance. So I can write the average inductor current is nothing but equal to the average output voltage upon the load resistance, right, where the average inductor current from this waveform you can write in terms of the area under this triangle, right. What is area under this triangle? The area under this triangle is half into base into height, let us say IL peak value divided by the total period Ts is equals to V naught by RL, right? Is that okay? Half into gamma times Ts into I peak is divided by Ts is the average current, and this average current must be equal to the average road current, which is V naught by RL. So by doing this, and you can further, if you want, you can substitute IL peak from this expression, which is V in minus V naught is equals to L times IL peak minus 0 upon VTS, right? In this region, V equal to L di by dt if you apply, then voltage is V in minus V naught is equals to L, di is I peak minus 0, right, divided by VTS. So you can substitute this I peak value from here to here, you get one equation in gamma, you have another equation in gamma already here. Let me write this as equation 1, this is equation 2, equation 3. You can solve for 1, 2, 3, you can find gamma, you can find output voltage, you can find all the things that you want to know. Is that okay? Any question? If you want, you can substitute it, you will get a quadratic, you may have to solve it, you may get two answers, you have to see which one may fit in, you have to do a little bit of exercise, but you can solve using 1, 2 and 3. After gets inductor. This period, okay? Yes, this will still flow and it will continue to discharge the capacitor. Yes, look at this circuit. There is a ripple current, there is an average current. This will only take the ripple current, this will only take the average current. So this average current has to be equal to this average current, right? Assume instead of this inductor you had a current source which was a square wave. So 10 ampere and 0 ampere. And the load is of course average 5 ampere. Still you can do the ripple of this flowing into this, the average value 5 ampere flowing into this, even though this current is 0 for some time, right? Any question? Just be careful, because this is what usually would happen, that when you are deriving expressions here, do not substitute VO is equal to D times Vin. Do not do that, because that equation is not valid in DCM, right? And that's a mistake which one might do, let's just simplify it, quickly solve it, you would end up substituting VO is equal to D times Vin, and that would not be correct, right? So don't do that. Any further questions? If we apply very less load, that means very large resistance, the gamma would approach closer and closer to Ts. Yes, yes. Gamma will approach closer to D. Yeah. So gamma Ts will approach to dTs. If we remove RL, okay, good question. Let's look at it. Okay, since you have asked it. But any other question? So he is asking some question which we'll try to understand. But any other question on this derivation part? Yeah. We have already derived gamma. What else you want? We already derived gamma. Equation 1, 2, 3, na? You can derive, go back and you derive, no problem. It's just 3 equations you have to solve, substitute and solve, nothing more than that. And you will get an expression which will be a quadratic expression, you can find the answer to that, you can eliminate, one of them would be correct, other one will be not correct, using some basic reasoning you can eliminate that. We'll give you a question in assignment on this one. Okay, then let's come to the interesting question. What would happen if your load resistance approaches infinity? What would happen if the load resistance approaches infinity? That is the question, right? If load resistance approaches infinity, right, the average current will become almost 0, assume it's open, right. That means this average current must be also equal to almost 0. Yeah, so of course this would move towards this side, correct. This gamma will move, will probably come very close to dTs. So if I have to draw the waveform, it would still rise, right, because when the switch is on, V in minus VO, the current will still rise, but then it will probably become 0 very nearby, very sharp, right, not straight line, very sharp. But this average still doesn't come out to be 0, right. So what will happen is, there is an average current here, this average suddenly you have removed. So now this average current will increase the average value of the capacitor for some time, it will be a transient phenomena, right. So this average current will flow, this DC current will flow into the capacitor voltage will keep on rising, right. If this voltage rises, when the switch is on, what happens to the slope? The slope will reduce. So the slope will keep reducing, and practically you would have this kind of condition when RL approaches infinity. That means this voltage would be almost equal to this voltage, your gamma would be almost equals to D, your input voltage will be almost equal to output voltage. When you close the switch, nothing will happen, maybe slightly current will rise. When you turn it off, nothing will happen, that small current will just reduce, if at all you have very close to infinite resistance at the output. So, and that's happening because your output voltage is now dependent on gamma or dependent on RL, right. So if your RL tends towards infinity, this would give you almost the same voltage as that of the input supply, irrespective of the duty cycle, right. I mean, it will of course change a little bit with duty cycle, but more or less it will give you the same output voltage as input voltage. It's out of syllabus question, but I can still explain, because I didn't want it to go that way, somebody asked me, therefore we went that way. So if your RL is infinity, right, there is no current which can flow here. So suddenly if you do it, whatever was the current here, the average current also, DC current also, KCL has to be satisfied, will go and dump into this cap. And if you push a DC current into the capacitor, the average voltage will rise. So this voltage keeps on rising and becomes very close to V in. Then switches on, this current rise is negligible. So no more average current dumping into the cap. That's how you would reach the steady state. So this voltage will become very close to this voltage, and this current will be almost 0, the current rise will be almost 0, gamma is equal to dTs. VL, yeah, during switch on, VL is almost 0, yeah. Okay, let's not talk too much about this case. Let's move on to something else now. So far we looked at one power electronic circuit which is used to reduce the voltage, right, and we saw one application. There are many other applications also for this circuit. Now we will move on to another circuit wherein the requirement is that the output voltage, the DC output voltage should be greater than the DC input voltage, right. This is the requirement which we will move on to now. Any application can you guys think of? Can you think of any application where you have input voltage, let's say lesser value, but you want output more, let's say anything, it could be 10 to 20, 200 to 400, whatever, anything. But can you think of an application in and around you where you want input voltage is low, the output is higher, and therefore we will then learn about this new type of converter. Go ahead. EV charging, not usually, but sometimes. Usually what happens is, if you have a grid, right, and it's a let's say an AC single phase, if you rectify it with the capacitor circuit, what would be the output voltage you would get with a large capacitor? If you rectify grid voltage with a large capacitor at the output, right, diode rectifier, what would be the average voltage across the capacitor? peak of the sine wave, right? So 325 into root 2, so maybe 400 volt. And let's say your battery is also 400, or battery is little bit for 50. If it's 50, it's anyways a buck converter or some sort of bucking is involved, right? Okay, so any other, there is one, by the way, use case of a boost converter in EV charging, which I didn't want you to bring in, but since you have told that name, let me tell it. And very interesting thing, right? You know about Porsche, right? The car, Porsche, whatever you want to call it. Porsche only, okay. Now, if you see two-wheelers, right, they have 50 volt bus on the vehicle. These four-wheelers have higher voltage bus or higher voltage battery pack. The reason is because they require more power, right? If you still want to operate a four-wheeler with a 50 volt, the current would be very large. So your conductors would be very, very thick, right? So of course, if the power increases, you want to have a higher voltage. Now most of the four-wheelers are 400 volt. One of the model of Porsche, which I don't remember the model name, which you can go and search, has a battery pack of 800 volt, right? But the chargers may not be capable of going up to 800 volt. They are usually up to 400, 500 volt, the public charging point, some of them. And therefore, there is an onboard DC to DC boost converter to take that 500 volt and still charge the battery of the vehicle, which is at 800 volt, right? So going from 500 to 800. Yeah, this operation we call it as boost. Yeah, but this is an application which is a bit rare. Any other application? Data center में क्या करोगे? Okay, ऐसे नहीं, थोड़ा सोच के. Okay. Yeah, so what he's saying is, you're talking about high voltage DC transmission. Yeah, you don't usually use boost because there you want to, increase it to very, very large amount. We'll see later on, boost is not really capable of doing very large boost, like, Spark plugs could be an application. Spark plugs you could also use like a pulsating output voltage, turn on, create a spark, then turn off. So there is a circuit which is specifically used for that. You can probably Google it and see, we won't do it here. Yeah, so they would provide an AC voltage to a small transformer, step it up, and that's what usually is used to provide the spark. Sometimes there are other circuits also which you can use, but the requirement there is a pulsating voltage at the output, right? So you create a spark, then you leave it, then again you create it, then you leave it. What about? Yeah, usually not, because there the battery voltage and the motor is usually designed together so that the motor is of the same voltage as that of battery. So you just use an inverter. Microphone. What is microphone? Oh, this one. I don't know. Okay, one application which I thought of, let me tell you, otherwise we'll just keep on talking about so many things, is solar generation, right? So, solar panels, right? One panel, it comes in different sizes and different powers, right? If I take one typical panel which is of 500 watt power, it comes with the voltage of about 40 volt, right? But these panels, of course the voltage is not constant, it keeps on changing. But let's say if this gives you 40 volt and now you want to use this panel to get an AC voltage of 230 volt, right? So what you would do is you would first connect, let's say 5-6 of these in series, right? And then maybe you let's say put 5, you get about 200 volt, and from that 200 volt you can use a boost converter and produce a 400 volt DC, and then you can use an inverter to get a 230 volt AC. Now inverter we don't know as of now, we'll probably learn about it little bit later in the course, but this case you would require a boost converter going from 200 volt to 400 volt, right, when you want to step up the DC voltage. I can always do it with an inverter and a transformer, but it will be bulkier because transformer would operate at 50 hertz, so not very high frequency, so high flux, you require thick core, right. So your transformer would be much bulkier, and therefore doing it this way could be much smaller size, maybe lower cost also, because you know transformer would require a lot of copper and a lot of iron and so on. Okay, is this application clear? Of course, this is one application. Another application I can just verbally tell you without going into too much detail is your UPS power supply backups, right. The battery voltages are high, but usually not very high, and again what you do is you use a battery of certain voltage and you boost it up, get a higher voltage, and then you connect the inverter, and then you get the power. So wherever you require increasing of the voltage, you use boost converter. Let's go in detail of boost converter. That's the DC to DC boost converter. What happened? Now what do we do with this? What should be the next step? You have to answer the same questions which we have asked before. What were those questions? The questions were, what is the average output voltage? What is the inductor current ripple? What is the output voltage ripple? What is the critical resistance? And maybe if you are keen on doing it, finding the output voltage in case of DCM as well, right. These are the things we would want to do for any power electronic converter that you would see for the first time, right. While understanding the basic output voltage and the ripple equations, what we end up also doing is understanding the basic operation, right. We know how the waveforms are, what are the different current waveforms, what are the different voltage waveforms, and so on. So, can you guys do it yourself, or do you want me to derive? Okay, I would on a serious note, I would not do this, right. You can try it out. I am sure if you see this in the exam, you can even do there impromptu. I would not do this. I would not even do this. Let's only derive the average voltage expressions, and rest of the things you can try, and if you have any questions, I can help you. Maybe we'll give them an exam, a question in the quiz or in the assignment also, right. So let's just try the output voltage average expression here. So this is D times Ts, this is Ts, switch is on, right, the MOSFET switch is on for the first D times Ts, and then it is off. From 0 to D times Ts for this time period, when the MOSFET is on, What is the voltage across the inductor? What is the voltage across the inductor for 0 to dts? So 0 to dts, what is the voltage across inductor for 0 to dts? What is the voltage across inductor from 0 to dts? What is the voltage across inductor from 0 to dts? When this switch is on, right? What is the voltage across inductor? When this switch is on, voltage across inductor is V in, right? Because this is short circuit, so you can write KVL in this loop. So 0 plus V in minus VL is equal to 0, right? So voltage across inductor is V in. And the current will flow in this loop. Since voltage is positive, the current will have a positive slope, V equal to L di by dt, and current would rise. Starting from some initial value, it goes to some value. And then for period of dts to ts, your voltage across inductor is, when you turn off the switch now, you have turned it, so inductor current was flowing in this direction, current was building up. Now you have turned off the switch. Now what will current do? Current of course cannot flow through this switch because it's off, it's open. So current will try to flow through the diode. As it flows through the diode, what is the voltage across inductor? V in minus VO. Alright. The second period, the voltage across inductor is V in minus V naught. Is this a positive value or a negative value? It's negative because the boost converter, so output voltage will be more than the input voltage. So V in minus V naught will be negative, and therefore the inductor current slope will be negative and the current will start falling. Right? This thing will be your delta IL, and this is your average inductor current. Is that okay? Any doubts so far? Apply volt second balance. Average voltage across inductor is equals to 0. That would give you, go ahead, can you apply the volt second balance? Of course, some of you know the answer anyways, but can you go ahead and apply the volt second balance? And give me the expression for output voltage. What is the, apply volt second balance and find the expression of output voltage, average output voltage. हमको पता है ना, निकालना. Just go by first principle, write it as an integral. That would give you a little bit of insight, right? Of course, you can still consider the same assumptions as we did before. What was the assumption we considered last time? Output voltage ripple is really small. Last time actually we didn't use it to calculate the average voltage, but now you would really need it. So you can consider the output voltage ripple to be very small. Of course, input is a constant, right? Everything is ideal. And apply the volt second balance. So V in is the voltage during 0 to dts plus V in minus V naught is the voltage during 1 minus d times ts equals to 0. If you solve it, you get VO is equals to V in upon 1 minus d. Yeah, all the time. Everywhere you want small ripple, so everywhere you use big capacitors. That depends, right? I mean, there are other things also. What I will try to do is that next time or sometime I will try to bring up actual power supply, so you can get a idea about the rough sizes and all. Of course, it would change from design to design. If you are talking about a converter for a train, the capacitors would be big. If you are talking about converter for your charger, your capacitors would be really tiny, right? So, it is relative, but is this okay? Any doubt so far? Alright. You know, in this case, other thing which you should realize and which you should notice is the average inductor current now is no longer equal to the average load current, which was the case in the previous converter, right? The average inductor current is no longer equal to the average load current. Is that okay? However, average load current is equals to the average diode current. So, and let me still refer to this circuit here, and I am writing equations here. So, you can see that in this case the average diode current will be equal to the average load current, which is V0 by RL, right? And what is relationship between average diode current and the average inductor current? This we can see here. In the waveform, I have drawn the inductor current waveform. I can also draw the diode current in this, right? So, what will be the diode current when switch S is on? How much is the diode current? 0, and when switch S is off, diode current is equal to inductor current, right? Same current. So, from this waveform, I can see that this is how the diode current would look like. Is that okay? This is how the diode current would look like. Is that fine? Where this is the IL max, this is the IL min, and there is, so this current is exactly same as the inductor current, and here there is no current in the diode. And therefore, I can write the average diode current is nothing but equal to, I can write it as, okay, IL max plus IL min divided by 2 into 1 minus V times Ts by Ts, which will cancel out, right. This is the average diode current, just by geometry if you see, this is the average diode current, where this is IL max, which is same as I diode max, and this is IL min, which is same as I diode min. Is that okay? And what about inductor current average value? The inductor current average value is nothing but equal to IL max plus IL min upon 2. And therefore, the relationship between these two things is is that okay? So, now between the inductor average current and the load current, average load current, there is a little bit of difference in terms of the final expression. Question? Right. Why the average diode current will be equal to V0 by RL? Okay, look at this picture here. There is a diode here, there is a capacitor here, there is a resistance here. Imagine instead of diode there is a current source, this is a capacitor, this current is almost constant. You got the answer, right? So, the ripple current will flow here, the average current of this is equal to average current of this. This is all because of capacitor. Any other doubt here? you could have derived it much faster. This is the average output current, by the way. You could have derived this relationship much faster, and you have done it as a part of the assignment also, right? We understand this is an ideal converter, so there is no losses happening here, and therefore, so ideal converter, that means no losses, and which means the average input voltage is constant, multiplied by the average input current is nothing but equal to the average output voltage, small ripple, output voltage almost constant, multiplied by the average output current, right? We already have expression for V in and V naught, right? This I in average is nothing but equal to inductor current average, because I in is this and inductor current is this, they are anyways in series, right? So you just substitute V naught is equal to 1 upon 1 minus D, and you will just quickly get the same expression, right, without really drawing those triangles and writing in that expression. There was an assignment question also previously, right, where you could have either done it directly by equating input average power is output average power, or you could have done it using this way, drawing the waveforms. Any doubts so far? Any questions? Okay, so first part is done. We have found the average output voltage. If you want to calculate inductor current ripple, you can do that, right? How will you do it? You know, when switch is on, this is the voltage across inductor, V equal to L di by dt. It will quickly give you the expression for inductor current ripple. So you can find this also. Output voltage ripple is going to be a little bit trickier now, quite tricky now, because now your diode current is this, and the ripple component of this flows in the capacitor, right? So you have to subtract the average output current from the diode current, and that is the current which will flow in the capacitor. So this diode current will shift below, right? So such that the average value is equal to 0, and that is what is flowing through the capacitor. A little bit complicated, but one can do it. Critical resistance, again, you know, you keep increasing the load resistance, you keep reducing the load current, increasing the resistance, your average output current will keep reducing, your average inductor current will also keep reducing, and there would be a point where inductor current would be at the critical condition, and that condition you can apply, you can find the critical resistance. Remember, CCM and DCM is always defined with respect to the inductor current. For example, if you look at the diode current remains 0, and it does remain 0 for quite some time, whatever you do. But that doesn't mean this converter is always in DCM or something like that, right? So CCM, DCM we always define in context to the inductor current. And you can define the critical resistance, you can find out the expression for critical resistance, right? Any question? Any doubt? Anything interesting? Okay. Yeah. What is the general frequency of switching in a boost converter? Again, depends on application. It can practically go from, I have seen some boost converters operating as low as 5 kilohertz, and of course I have seen boost converter operating at megahertz. So depending on power, depending on voltage level, current level, you can, different applications may have different frequencies, right? So going from 5 kilohertz to megahertz, right? So those things are there, which, you know, in this basic course we don't really cover those things. At a later advanced course you can go into those details, you know. So for example, here there are, in reality you don't have a pure inductor, in reality you never have a pure switch, you never have a pure diode, so many things are there, but at this point this is very close to reality. It's not like we are really far away from reality, it's very close to reality, but it's not exactly same as what happens in the reality. So some of those smaller things, you know, you can keep learning, and that's endless, right? You know, not even in 4 years, 10 years, 15 years, 20 years, you can still keep learning. I still learn quite a few things now. But what I'm saying is, it's like very close to reality. It's not like we are really far away from the reality. Output voltage in discontinuous conduction mode, again you can find out, I am sure. Yeah. The idea here is that last time we saw a buck converter, today you saw a boost converter, tomorrow you will see some buck boost converter, right? We should not just keep repeating the same thing, right? You have learned the art, you have learned the method, you just apply the methods to any converter that you see, right? Our TAs come up with new circuit, new inverter or new converter, DC-DC, give you in the quiz, don't say it's out of syllabus. You have learned the method to analyze it, just analyze it using the same method. And therefore, no point in remembering any of these formula. Don't remember any of these formula, it will not help you at all. I am not going to ask you what is the output average voltage for 5 volt input and duty cycle of 0.25. Doesn't make sense, right? What you should learn here is that how we have derived these things for buck converter, where we have gone in little bit more detail, and now you should be able to apply the same procedure to any other new converter that you may see anywhere. Right? Just because we are talking, there is something called as a buck boost converter, which can do buck also and which can do boost also. Have you guys heard about this guy called buck boost converter? All of you have heard about it, very nice. So you can go back, you can just relook at the circuit. Let me write it on the board so that you should not say that I have not taught you buck boost converter. So buck boost Yeah. So, the idea is that you should be able to analyze these circuits, right? And I think with that we are almost towards the end. Right. So, I'll not again, we cannot go in too much detail in this course, but if you honestly ask me, if I looking at this circuit, could you have predicted this would have been a boost converter? Anyone, without writing these equations, without me telling you, could you have just looked at this converter and you could have said that this is a boost converter? Or at least not the name, but you could have said the output voltage is more than the input average voltage. Anyone? You can actually, just look at it carefully. This is what we did with buck converter, if you remember. The way when we approached it using a switching element and then a filter, just look at it in the same way, right? Look at it in the same way. Can you say this is a boost actually, just by that principle? Anyone looking at it in that way? No one, some people are looking in phone, others are looking here, but maybe dreaming something else. You see, this is a switching element. When switch is on, this voltage is 0. When switch is off, diode is on, so this voltage is output voltage. So what is the average voltage here? Output voltage multiplied by the duty cycle of the diode, which is 1 minus D, so to say, right? So the average voltage here is less than the output voltage, all of you agree? And this average voltage must be equal to this average voltage. So by looking at it also, you can actually quickly see that this guy is not going to be anything else but a boost converter. So you can look at that way. Of course, life does become complicated as we move forward and look at more complicated circuits. But by intuition also, you could have said that, this is the same switching element, this is the same switch which we have drawn, right? In fact, if you really look it closely, you would understand that this is nothing but a mirror image of what we have drawn before. Right? If you look it closely, if I had not drawn these switches, if I have drawn it like this and this, right, it would be a mirror image of what we have drawn. So the way we were going from 10 to 20, now we are going from 20 to 10, same thing again, right. So there is, of course it does take considerable amount of time to develop the intuition, but there is a logic, there is a way of looking at the circuits without really writing too many equations as well, but maybe not for this course, more than this, okay. So with that, let's sort of conclude today's class. We are more or less completed with basic buck boost converters, right? Just before we end, one quick question so that I can prepare for my next class. Have you guys heard something called as a flyback converter? Yes, yes. How many of you have yes? Raise your hand. No. Okay.